It's time to begin the webinar. Welcome to the Microsemi webinar, 5G Network Densification, Preparing Your Timing Architecture, hosted by RCR Wireless News. I am your host, Susan Rambo, 5G editor at RCR Wireless. Our panelists today are Barry Dropping and Jim Olson. Barry Dropping is the Senior Director of Product Line Management at Microsemi. Hello, Barry.
Good morning, Susan. Thank you and RCR for hosting this important event today and the invitation to join you.
Thank you. It's nice to have you here. And then we also have Jim Olson. He's the Director of North America Solutions Architect at Microsemi. Hi, Jim.
Good morning, Susan, and welcome to everyone attending the webinar this morning.
Thanks, Jim. So here's our agenda for today's webinar. I will give you a brief update on the 5G network densification, and we'll ask our panelists to describe the issues in network densification in more detail. In this webinar, you will learn the challenges of network timing services for 5G networks that operators must consider, including the key concepts of setting and maintaining and holding phase, technical approaches to cost-effectively and reliably solving these stringent time phase requirements, and an explanation of why PTP Grandmaster at the network edge and assisted partial timing support at the network core are crucial elements for any 5G deployment. We will have time at the end to answer questions, so please enter your questions in the question box now and throughout our conversation as you are thinking of your questions. A copy of this webinar will be posted with the slides to our website shortly after the show. So, network densification for 5G. What it's meant to do is to add capacity to existing networks. Typical methods that are happening now under 4G are adding more small cells to a network to carry the signal, especially millimeter wave, farther. Centralizing or virtualizing the radio access network, known as CRAN, is also another option. It's building capacity without intercell interference. So where it's needed most, obviously, is in areas with high concentration of mobile users, such as urban areas and large public venues. And why we need it: the explosion of applications growth, the massive bandwidth that's needed for 5G networks is for both fixed and mobile wireless is a high priority for operators. So just a brief summary. Network densification using small cells has been happening in 4G LTE already. In 5G, we're seeing trials of small cells, or HETNets, in China, India, South Korea, and the US. For example, AT&T's Project AirGig trials in Georgia, and the US company Mobility's installation of DOS and small cells in an LA stadium. Products that we're seeing now, such as Qualcomm's announcement yesterday, that they are going to be sampling a 5G NR version of their FSM chips and solutions for small cells in 2019. The announcement yesterday reassured people that 5G really is a priority with Qualcomm. We're seeing all sorts of announcements like that. And then their standards happenings now. The 3GPP standards have been addressing small cells for years, as you probably know. But in June 2018, the 5G standalone standards are scheduled to be completed. Just this week, Samsung is hosting the meeting to complete 5G Phase 1 standards. So what we need to do next is finish the main standards, of course, and then expand the trials and the networks. So today's webinar will help network operators understand some of the fundamental issues with synchronization that needs to happen in the network densification. So let's hear what Microsemi has to say. So Barry, can you talk to us about where sync comes from in these networks?
Sure, Susan, thank you. Yes, we really use this model to talk about the timing and the source and the distribution of sync. This is one of the key models we use in all of our discussions and technology exploring technologies with our customers. But starting in the upper left, really the source of synchronization for all the wireless networks is GPS. This really is the source of time traceability. The GPS network of satellites carry very, very accurate clocks, and this is the way to establish your time and phase synchronization traceability to UTC, Universal Coordinated Time. So GPS is the workhorse for synchronization. That's the source, and then it generates not only the time and phase, but also the frequency. Then the clock needs to be distributed out to the endpoints where you need it. So you have your good core source clock, and then you distribute it, inject it into the network. Then the operators carry it across their transport network. This is the backhaul and evolving into the front haul networks to carry all the traffic. It also carries the clock timestamps out to the end application. The end application was where you have a small clock to recover that clock. Now, along the way, there are little errors that build up. There's jitter, there's things like asymmetry. We'll talk about those, later today. But the end clock, filters all that and then holds the application specific requirements, which we'll talk about, and those are getting tighter and tighter. You also see the option at the end clock is you could also put a GPS there. In many cases, the GPS is available there. There's line of sight to the sky, so you can lock the in station with the GPS. Then you're using the network clock for your backup and the holdover in the event that the local clock is lost. The trend we're seeing moving forward, however, is that the end clocks are becoming ever and ever denser, as you talked about, and they're going in indoor locations. So there, it's not able to be able to see line of sight to the sky and use GPS. So increasingly, the end stations are going to rely on the source clock coming across the network for their time and frequency synchronization. And then, that gives rise to a lot of standards work that is being done to engineer how the transport network will carry the source clock out to the end stations.
Okay, thanks. Speaking of standards, are there standards that dictate where the time comes from? Are there standards that the industry is adopting?
Yeah, absolutely. And that's really happening today with LTE. On the next slide, I've got a couple of standards I wanted to explore. These are the two main standards for distribution of time and phase in wireless networks. These standards are written as what are known as PTP profiles by the ITU. And the PTP is IEEE 1588 Precision Time Protocol. That's the protocol used to carry the clock across the network. The two standards, the upper track is known as G8275.1. That's known as full on-pass support. And the really neat thing about this standard is if you're building a new network, a greenfield type of a network for your front haul or your backhaul network, you can engineer clocks into every element along the way. So you see that noted with a little icon that says BC and Sync E. That stands for boundary clock and Sync E. That's generally a chip set, a little clock that goes in every element along the way, and that helps transport the phase and timing across the network. The lower one is its sister standard. That's called G8275.2. That's called partial on-pass support. And this is really designed to use your existing network. So if you're an operator and you're not building up a new network, this standard says, how do I carry that clock across my existing network? Where you say the boundary clock and the synchronous Ethernet, that's optional. You can, if you have it, you could use it. If you have it in some sites, you can use that. But the key to this is they both follow the same model where you have a core, what's known as a PTP grandmaster. That's their source clock that we talked about in the prior model. And that injects, takes the signal off of the GPS antenna, injects it into the network, and then the PTP slave clock out on the far end is where that clock is recovered, right? So these are the two main standards being used today for LTE-Advanced services, and they're really designed to be ready to pave the way for 5G as the requirements just get tighter and tighter.
Interesting. So Jim, can you tell us about Microsemi's view of 5G?
Yeah, thank you, Susan. So from a Microsemi perspective, if you look at 5G from a timing perspective, there's a couple of key takeaways on this slide here. The first one would be in the bottom right-hand corner, where we talk about low latency solutions. So for 5G, there's going to be tighter latency requirements than 4G, moving probably from milliseconds to microseconds. So how do you achieve that? One way to achieve that is by distributing intelligence across the network and moving some intelligent components into the radios themselves. The other way to do it is going to be to increase the speed of the transport equipment and the switching equipment, which is already underway in the initial testing we see for 5G. In the middle, we talk about scalable synchronization and scalable synchronization solutions. If we're going to exponentially increase the amount of radios in the network, then there's going to be a lot more radios. And if we use, as Barry said, GPS as an option in the radios, and you have a lot of radios in the same cluster with GPS, and that GPS were to fail, you're going to introduce interference into the other radios in that cluster, and that radio will have to be taken out of service. So in many cases for 5G, it may make more sense to move to a network-based time and delivery method, which is really a 1588 or PTP-based solution. Of course, if we move in that direction, there's always the option to use both GPS and then use PTP or a network-based delivery timing service as a backup option. But certainly a common source to the radios means that if you have something like a grandmaster and a common source of timing for all of the radios, if you have a GPS failure on the grandmaster, all of the radios will remain in phase with each other, and the relative phase alignment between the radios can be maintained, and you won't have to take those radios out of service. Let's move to the next slide, please. So we talk here about some 5G timing trends, and what does 5G mean to different operators or vendors or people in the communications industry. We see two trends emerging here. One will happen before the other, and it's happening already, especially in some of the mature telecom markets, is the concept of fixed wireless for broadband services. Fixed wireless uses the higher spectrum of 3.5 to 60 gigahertz, and there's some level of ability with the broadband service that you can use with emerging technology called attach or reattach, where you can access these fixed wireless spots from different places if you have the device attached to your phone or your computer. But if you look at the term down here, LTE-TDD, or time division duplex, LTE-TDD technology is very similar to what we see going into the CRAN, but LTE-TDD technology is very similar requirements from a timing perspective to what we had in the CDMA networks of the past. That's associated with the plus or minus 1.5 microsecond phase or absolute time alignment timing requirement. So if we move back in time, 10 or 15 years, and we look at a CDMA base station, CDMA base stations had this same timing requirement, and the CDMA base stations all had GPS receivers in the base stations, and they also had rubidium atomic clock oscillators. So that if the GPS signal was no longer available, we could back up the phase requirements and hold that phase with a rubidium atomic clock. Rubidium atomic clock oscillators are fairly expensive. So if we fast forward to today, rubidium atomic clock oscillators are not really an option in a base station or a radio to hold phase if we lose GPS. It's simply too expensive. And the number of cells we're putting out there, it's just not a good cost-effective approach any longer. But if you look at the evolution of timing in base stations, for frequency, there was always two possibilities. We could put GPS in the base station, or in the past, for frequency modes, we could use clock recovery at the physical layer for frequency using T1 or E1 circuits. Well, those T1 or E1 circuits are typically not available anymore as we move to Ethernet transport. So we have to have a different model. So for frequency, if we don't use GPS, or as a backup to use GPS, we've introduced synchronous Ethernet or 1588 PTP precision time protocol as a primary or secondary source of frequency reconstruction. As we move into a new era with LTE-TDD and also LTE-Advanced features, and we have additional requirements beyond frequency, such as phase alignment of the radios, and rubidium is really not an option. We do have PTP as that option to either back up for phase or as a primary source of phase to set, maintain, or hold phase at the edge of the network. So if we look at network timing delivery models, there's two main things that impact this, and that is asymmetry and packet delay variation. So that's a challenge in today's networks. And if we look towards the bottom of this slide, as we move from CPRI to Ethernet radios, we see that latency is extremely important. As we move from CPRI to Ethernet, we will see an introduction of more and more PTP or synchronous Ethernet-centric timing delivery mechanisms. But as we move into this model with new low latency switching and routing technology, PTP performance will be dramatically improved when we move the PTP flows through these low latency switches. Microsemi has been doing quite a bit of testing on some of these new switches, especially in the front haul domain, and we are seeing drastic improvements over the last couple of years from previous testing we did at 1 gigabit speeds to the testing we've done at 10 gigabit or higher. Some of these new low latency switches are yielding results as good as 20 or 10 nanoseconds of time error through one switch. So this is phenomenal new technology, and this will really help PTP performance and the model using network timing as a timing delivery mechanism. So on the next slide, please. So we have a couple of illustrations here that show the evolution of timing in 5G. This is really a CRAN diagram where we show the introduction of PTP slaves being introduced into the baseband units we show here in a baseband pool. Now, one option could always be having GPS in the radio heads, or using this model we show with the PTP slave in the BBU as the primary or a secondary backup to GPS in the radio heads themselves. If we look at this model, we see that the PTP slaves located in the BBU will recover clock from a grandmaster clock, and in this case, in this slide, we show that grandmaster clock in the middle as a gateway clock. And so why do we call it a gateway clock instead of a grandmaster clock? That's because we have some attributes or functions in this clock that are beyond the normal attributes or functions of a grandmaster clock. And we'll talk a little bit more about that later in the presentation. But in this model, we show timing delivery using PTP flow into the BBU PTP slave. And from the BBU to the remote radio heads, we have a CPRI connection, or a common public radio interface connection, into the radios. This is what carries the timing from the BBU into the radio head itself. CPRI is very TDM-like and very deterministic, so we can reconstruct frequency and deliver phase extremely accurately into the radio heads. So that is the timing delivery mechanism. Works very well and should meet all the requirements moving into the 5G world. The other component we see on here is a grandmaster clock located further back in the core of the network. From this grandmaster clock to the gateway clock, we show an APTS, or assisted partial timing support flow, as a PTP or 1588 input into that gateway clock. We're going to talk about that function and how it's used to maintain phase in that gateway clock at the edge of the network if we were to lose GPS availability or have tracking issues with GPS at that gateway clock at the edge of the network. So let's move to the next slide. So this slide kind of advances into the 5G world of the future. When we move to eCPRI, which is more of an Ethernet model, where we will evolve the connection between the baseband units, or in the future, which will be virtual baseband units, into the radio heads from CPRI to Ethernet. So this is certainly a move to Ethernet radios and adding intelligence into the radio heads themselves. It'll be interesting to see as we evolve into the 5G world. We will see a lot of the macro eNode Bs evolve to remote radio heads with these Ethernet radio models. But it'll be extremely interesting to see in the small cell world if small cells evolve to remote radio heads with Ethernet radio technology, or if they will remain a cell with co-located baseband units and radios in the same location. It'll be a very interesting evolution. But as you can see in this slide, we are moving the PTP slaves from the BBU into the remote radio heads themselves for Ethernet radios. This model here is showing a CU or DU location with the same gateway clock we showed in the CRAN model with the BBU pool. So this is a very cost-effective approach to timing for remote radio heads with Ethernet transport, because if you place a gateway clock in a CRAN site or CRAN hub today, and you evolve your network to Ethernet into the Ethernet radios, you will already have in place what you need from a timing component perspective to meet the requirements today and in the future. And again, if you notice on this slide, we show that the Grandmaster clock is backing up that gateway clock at the edge of the network with an APTS PTP flow as a PTP input in the gateway clock. Again, nothing changes with the evolution to Ethernet radios. We can leverage this investment into the future. And if we look at the timing requirements evolution, the timing requirements for the standards will evolve based on the features we are going to use in the radios themselves. We will have both relative and absolute time requirements in the radio heads, and with the new low latency switches with high performance PTP along with synchronous Ethernet, we should have no problem meeting the timing requirements in the future for both CPRI, CRAN based models, and Ethernet radio models that we show on this particular slide. Barry, could you possibly help us with a more detailed understanding of this APTS technology and how it works?
Sure, Jim, I will do that. On the next slide, please, I'll cover that. Now this move to eCPRI is something we see a lot of our customers planning for today. What they tend to have in their networks are core clocks today to drive their LTE, so that clock already exists. The nice thing about the standard that is set in place for assisted partial timing support is it allows clocks to back each other up across the network. So Jim talked about APTS, that's assisted partial timing support. What we're also introducing on this slide is a concept of automatic asymmetry compensation. As the timestamps go across the network, I mentioned earlier they pick up little errors, and one of the key errors is asymmetry. Asymmetry is just that, you know, the time to transit in the downstream is different than it is in the upstream, and that asymmetry in terms of time transfer can introduce an error. The nice thing about assisted partial timing support is that that gateway clock can lean on or take a backup from its core clock that already exists today. That's the big PTP Grandmaster clock used in most of the LTE networks that are out there today. That's sending the timestamps out, and the gateway site can receive those timestamps and then calibrate it. So now it has a calibrated backup. It basically removes the asymmetry. Now, Microsemi has some patents on that type of technology. We follow the standard for APTS, that's a standard, and then we add the capability to automatically calibrate out the asymmetry. And as noted here, we can do that for path rearrangements. That's a real world engineering phenomena that the network planners have to plan for. You know, they say, okay, I've got my backup, that's all fine, but what if there's a path rearrangement and then it takes a different route? What our technology does is it's going to profile those routes, automatically build a table, and on the fly, it's going to be looking at a route change, picking up what we call our timing signature of that route change, and then switching to a different asymmetry compensation value. We've got a whole white paper coming into generation about that right now, and that's an interesting one to go through that technology and how it really applies. The big benefit of all this to I would say to the customers is they have their core clocks today. That's a big investment they've made for LTE. And now when they go to add the gateway clocks that are needed for LTE-Advanced services, BBU pools like Jim talked about, getting ready for eCPRI, and then on into 5G, as things just get tighter and tighter in terms of timing, they can add that gateway clock function, and it takes its calibrated backup from the core clock they already have. So that's a little snapshot on how that works. I'll talk now about the kind of functional view of what is a gateway clock. So on the next slide, we introduce a block diagram here that talks, what is this new class of clock evolving for 5G that we call a gateway. It's really a simple functional block diagram where you have, its input side and then its distribution side. And those are firewalled inside the clock because you really want to have that isolation and protection that on your timescale generation that's inside the clock is it takes the time from its local GNSS receiver. So it's picking that time off the satellites. You concentrate that GPS location where the gateway clock is, and that's what sets the timing for its sector of the network. And that gives you what's known as primary reference time clock traceability to plus minus 100 nanoseconds from UTC. So very, very accurate clock generating that time scale. Now that you've generated the time scale, you need to hold time. If you lose your GPS for whatever reason, the antenna gets knocked down or there's an interference signal to it, real world phenomenon like that occur, then you're using the PTP feed coming from the network core clock as your calibrated backup. Obviously, you'll generate alarm. Someone will go out there, repair the antenna or remedy whatever the situation is. But while that's being done, you're protected. All the downstream elements don't even know that the GPS was lost. They're just seeing good precise timing maintained, and all those elements downstream kind of stay locked to this gateway clock function. Over on the distribution side, that's where it's generating PTP and synchronous Ethernet, sending those protocols out over the network to give you that time to the end points that need it. The radio heads, the small cells, whatever they might be, they all have clocks in it, and they need that PTP and sync E backup. So that's the functional view of the gateway clock. On the next slide, I'll go through some of the key attributes. And we'll really break this down into 4 key areas. The first one is resilience. The whole point of the gateway clock is that you tie all the nodes below it. There could be hundreds of nodes and radio heads that need to have the common clock. That clock needs to be very, very reliable. So we put a lot of effort into making sure that clock is reliable. It's got multiple sources of backup synchronization, and it has internal oscillators too for its own holdover protection. And you concentrate that oscillator inside the gateway clock rather than trying to put an expensive oscillator in every small cell, for example. That's just not cost effective to handle the densification that Susan talked about as it's coming forward. The other one that we focus on is scalable performance. So, as the network start, you need to have the capacity in that clock to be able to scale up and handle the load that densification is going to place on it. So a lot of effort goes into that scalable performance. And then we also have extensive Ethernet fan out, multiple ports, multiple protocols supported. So a lot of flexibility for the Ethernet standards as all these new standards are evolving. I showed 2 of them earlier, but there are several others that are in use today. So a gateway is going to take a concentrated point clock and distribute whatever protocols are needed out of it. So that means it needs to have multiple ports. And at the bottom, we talked about SSU function. That's a little bit of a legacy timing requirements because carriers have lots of pieces and elements in their network that need not only the next gen timing feeds, but also they need to be able to support the current TDM type of timing feeds. In the US, that would be a traditional T1 sync reference. So a lot of capability built into these clocks. On the next slide, I'll go into a little more detail on our implementation of this. This is our newest product. We've just introduced this product. It's called our Time Provider 4100. It is a full gateway clock function that we've talked about. It broke down some of the distribution timing flows. It does all of the precision time protocol standards that we talked about from the ITU. It also provides local NTP, network time protocol, used for logging events and everything else. And then it has a lot of physical timing flows like like a T1 or an E1 or a 1 PPS signal, a time of day reference, a lot of flexibility. On the input section, this is where we talked about the GNSS. That's how you set time in the gateway clock, and then you protect time with backup signals. And PTP backup with the APTS is the key backup and the key attribute of how this clock plugs into the network and connects to the core clock that already exists and gives you a higher level of resilience and protection. And it's all about that protection that we see on the right side. You use the network for protection, you use internal oscillator for protection, and you put all that protection in your gateway clock, so all the base stations downstream from it, or small cells, or radio heads, they're all protected from the gateway clock. Jim talked about that concept earlier, that if one clock starts to drift away from the other, that's where you have problems, because one base station drifts away from the other, they start to interfere with each other, and then they have to be taken offline, right? If you let them all follow and stay locked to a common gateway clock, if the gateway clock takes its backup, if it starts to drift a little bit, it's not a problem for the network, because all the elements, all the base stations stay aligned to the gateway clock. So they have their common time reference. That's a key planning and network engineering principle that we recommend to customers. All right, I've got a couple more slides just going through some of the attributes. These are some of the key technologies, if you will, that are inside the gateway clocks with the assisted partial timing support to really make sure it's very robust and highly reliable. We have different oscillator choices, including a full atomic clock inside of there. That's known as a miniature atomic clock based on rubidium. These are commonly done in the gateway locations to have a very, very good backup. Now all of the base stations connected to it share that good rubidium oscillator for backup. They don't have to have their own precision oscillator or expensive OCXO inside of them. The GPS antenna, that's where you get your UTC traceability. You concentrate that on the gateway clock location, and then you use the network to do that protection, that backup feed out to the core clock, which gives you that APTS backup. That's something that we follow the standard. It's noted here as G8273.1. And then I talked about the added value that we have is the automatic asymmetry compensation, which really makes it robust to a network rearrangement. That's the key one to that. So a lot of effort and technology goes into taking the pedigree of our core clocks, concentrating those into our new family of gateway clocks, and giving a very, very robust gateway clock to protect the network and rely on a backup feed to the core clock that already exists. I have one more I wanted to talk about, which is a new one that the customers are really asking us to focus on, and that is the monitoring. In the core clock, that's a clock that stands at the core. It takes the synchronization and distributes it. So you just monitor there the performance of the clock. Is it locked? Is everything healthy? But in the gateway location, you need to do a lot more than that. You need to monitor, okay, how is that backup link? Am I receiving good sync of it? If I needed to switch to it, is it available? And the monitoring is offered in two kind of phases. The first phase on the left is the internal monitoring that the clock does itself. It can do a lot of measurement and analysis, and customers ask for this because they really want to have that capability when they're engineering their network and looking at their network topologies, their types of backhaul, what kind of sync can they get across a microwave backhaul, what kind of sync can they get across an Ethernet backhaul, et cetera, et cetera. So they do a lot of measurement and analysis when they plan the network deployment rules and guidelines. So that's all done internal to the clock. We've got a full GUI. We can put in metrics and monitoring and give you profiles right off the device of what's happening. So that's kind of that hands-on phase where the engineers are deciding, how are we going to engineer our network? Where are we going to put our clocks? How are we going to set our rules? Then the clocks go into deployment. Now you've got dozens or hundreds of these clocks out there. Then you use a centralized management system. And that's what we show on the right side here. So that's pulling up all kinds of monitoring metrics about the health of the sync network, the capacity, the load. It's generating any alarms. You can set thresholds and click, 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 drill down to actionable steps from a network management system, just using the advantage of the internal monitoring that are in the clock. Something very important for these gateway locations. And we really view this as critical for 5G performance assurance. You need to know those clocks are in the right location, they're functioning properly, and all their backups are in good health. So that's something that goes into the advanced monitoring that we've engineered into these clocks. Okay. Well, with that, I'll take us to a summary slide. You know, the key for densification really is that we need to make sure you're ready. You're making your network ready, not just for the LTE and LTE-Advanced services today, but putting the right investments in place that get you ready for 5G, because that's really going to be an evolving path, not a discrete event. So 5G, as we talked about, introduces some really challenging timing requirements that are going to need to be met. The key ways to meet those requirements are shown here as either GNSS integration into all the radios, and where you can get line of sight, that's a good option. But you would always want to have a backup to it using a PTP flow to that. And then as things get denser and denser, there's just going to be, you know, thousands and thousands of locations where you just can't see line of sight to the sky to put the GPS in. So second choice is to use network-based timing service, comprised of two elements: the IEEE 1588 precision time protocol standard that we talked about, and synchronous Ethernet. Both of those are in use today for LTE networks. Or you could do a combination of the both, as we talked about, and that's what the gateway clock does. It combines both of those, blends them together, and gives you a very protected clock that could then network feed the PTP flow out to the endpoints using that GPS that is at the gateway location. So we really view that the really most cost-effective planning and reliable method is to utilize PTP plus SYNC-E, and then have that in a source clock that is at the gateway location. So you've got the GPS coming into that source clock, and then you distribute with the PTP and SYNC-E feeds, and take advantage of the standards that give you that assisted partial timing support, so you get the backup, the strength of your big core clock that's in the network today to protect your gateway clocks, and in turn protecting all the endpoints out in the network. All right, well, with that, I just wanted to review and open us up for questions for Jim, myself, and Susan.
Thank you, Jim and Barry. That was fascinating and very complex. I'll just start with one question, but I want to remind the audience to go ahead and put your questions in the question box. We have about 20 minutes for questions. So the first question is, what are the biggest challenges to a network-based timing delivery service, and how do you overcome those challenges?
Yeah, Susan, this is Jim. I think I'll try to help answer that question, and this may also answer some of the broader questions we might see from the audience. So it'll take me a few minutes, but so Barry talked a little bit earlier about the standards, and he had a standard slide up there that showed two different models. One model being a full on-pass support model, and the other model a partial on-pass support model. So what is the differences between the two models? The full on-pass support model uses boundary clocks and possibly synchronous Ethernet into every switch or node between the grandmaster and the PTP slave. And this helps mitigate packet delay variation and network asymmetry. The other model he showed, partial timing on-pass support, tackles the problem a little bit differently. In that model, we use QoS for the PTP flows, and we differentiate either at layer 3 QoS or layer 2 differentiation in class of service, where we give the PTP packets high priority. This helps us mitigate packet delay variation. And in addition to that, we show with the gateway clock, we're moving the grandmaster function closer to the PTP slaves themselves. And this helps mitigate the problem of asymmetry. So first of all, what is the difference between asymmetry and packet delay variation, and how do they impact timing performance? So packet delay variation, or packet jitter, is a big problem in the frequency reconstruction world, but it can also impact phase delivery to some extent. So packet delay variation can be mitigated with QoS on the PTP flows in that partial on-path timing support model, or also in the full on-path support model using boundary clocks. Asymmetry is much more difficult or a much bigger challenge to overcome. Asymmetry is the difference in the delay in the forward and reverse direction between the source of the timer, the grandmaster, and the PTP slaves in the radios or the baseband units themselves. And it's much more difficult to solve because a time transfer methodology like PTP or 1588 can only assume that the network connection is symmetrical because it doesn't know what level of asymmetry there is. So asymmetry is related to performance for setting time and phase at the edge of the network. But as Barry showed in his slide on APTS, or Assisted Partial Timing Support, once we have set time or phase at the edge of the network using either standards-based model, it's much easier to maintain that phase when we use a technology like APTS and back it up from the core, because the amount of asymmetry can be calculated and corrected for between that gateway clock we show and the grandmaster clock we showed further back in the core of the network. So we can maintain time at the edge of the network even with large levels of asymmetry. So these challenges of asymmetry, which mainly affects our ability to recover time and phase at the edge of the network, and PDV, which mainly is a problem for frequency reconstruction, you have to have some mechanism in place to overcome these challenges, either using full or partial on-path support.
Okay. Okay, thanks for that. So here's a question for Barry. What would be the holdover duration for time provider 4100 in case PTP or GPS connection is lost?
Sure, that's a good question. That is a typical question we get from the network engineers who are doing their planning for their backup, right? So the first thing we recommend is the assisted partial timing support. So you really don't go into what I would call a holdover where you have to rely on your local oscillator. You're using that calibrated link back to the core. We see that holding well within 200 nanoseconds over extended periods of time, because as long as you have that backup signal, you're going to hold that phase. You know, the phase is originally set and calibrated from the GPS. When the GPS goes away, you use the network feed to hold the phase. So that'll give you a really extended, holdover for period of, period of weeks. If the next layer of defense is the local oscillator. So if you lost your source clock, or if you're in an area of the network where you're really isolated from any source clock, then you're going to tend to want to have a more higher performance oscillator in the gateway clock itself. So we offer 3 grades of oscillator there, and their holdover ranges, are kind of tailored to what you need. For these LTE-Advanced and 5G, the holdover budgets are very, very tight. The end applications today need to hold 1.1 microseconds delivery to those endpoints. So there we advise the use of a rubidium oscillator, and that will give you well in excess of a day of holdover. So you'll generate an alarm, you'll need to open up a service ticket, and go out there and restore the GPS connection. You have 24 hours to do that. That's what typically people will engineer to. Rubidium, of course, can extend that to longer durations as well. Typical performance we're seeing is in the area of a few hundred nanoseconds across a day. So I hope that gives you some parameters of what you would typically see and what your engineering limits should be.
Okay, great, thanks. And here's one for Jim. Is 5G expected to have phase sync requirement much lower than plus or minus 1.5 microseconds? Let's talk about for most cases, not just the edge cases.
Yeah, Susan, that's a good question. And so if you look at the evolution in the standards today and what's coming out of the XRAN forum or the eCPRI Alliance and these types of things, it looks like there'll be two phase requirements, and this is a fundamental understanding of timing, is the absolute time requirements to UTC traceable time and phase probably will not change. They will still be plus or minus 1.5 microseconds, which is what they have been for 4G as well. But what's being introduced now is the concept of relative phase between radio heads in a cluster. And there is some debate between operators, vendors, and standards people as to how tight those specifications will become. If you look at the latest information out of the XRAN, it talks about relative phase requirements between radio heads in the same cluster being as tight as 175 nanoseconds. And if you look at some of the information being introduced into the standards bodies, some say for different features such as coordinated multi-point, they may even be tighter. I don't think that debate is over, and what the actual phase requirements for 5G will probably depend on the features deployed in the radios themselves. But right now, I think that plus or minus 175 nanoseconds for relative phase requirement between radio heads in a cluster, along with the absolute time error requirement of plus or minus 1.5 microseconds, is the most realistic numbers we see today.
Okay. So what is the delay and phase requirements of eCPRI? Jim?
So again, that has to do with the features deployed in the radios. And one thing we know for sure, if you look at the new low latency switches and the different models of approaching synchronization, these requirements can be met by putting GPS receivers in the baseband units or remote radio heads, or with the network timing delivery service.
How many slaves can TP 4100 support?
Yeah, this is Barry. So we offered in a scalable performance, and you dimension that in two profiles. One profile where it's a unicast, like the 8275.2 that we talked about. There we can scale up to 512 slave devices in one single gateway clock location. The other profile uses a multicast, so that really scales up, as many as you put out, as many clients as you put out there to listen to that multicast flow can be supported. So it really depends on which of the two profiles you're supporting out of the gateway clock location. And the nice thing about a gateway clock is you can assign different services to different ports and share that capacity amongst the different ports. So the straight unicast is 512 clients, and then with the multicast, it just scales up with assigning multi-class flows and however many clients are going to listen to that flow.
Okay, and this question is for Jim. With gateway clock, can I spend the entire plus or minus 1.5 microsecond budget between gateway clock and end application? In other words, the time error contributed by the non-participating nodes between core PRTC and gateway clock don't count towards the 1.5 microsecond budget?
Actually, wherever the source, you introduce the source of time, and it's, as Barry said earlier in our starting slides, it's going to be GPS based. Between there and the error interface is the total error budget accumulation. So wherever we introduce the source of clock, whether it's in a full on-pass support model, which would be normally further back in the network, or in the partial on-pass support model, which is closer to the PTP slaves, that error budget of plus or minus 1.5 will be between the source and the error interface. And then we can subtract that value of the relative phase requirement of the radio heads from that total error budget, and that will give us the time error budget between the source clock and the radio heads.
Okay. So I have a question. How long do you see it taking CRAN to fulfill its promise for 5G?
Yeah, this is Jim. I'll try to answer that question, but that's a really tough question. One of the things we see is that the different markets globally are evolving at a different pace or rate. If you look at CRAN in the US, the big operators in the US, and also you go to Korea or Japan or some of the more advanced markets like China, we see this CRAN concept with BBU pooling already in place, and the deployments are occurring now. In other parts of the world where they don't have fiber-rich environments, the evolution to CRAN and also the evolution to 5G is going to be much, much slower. We see, and as we visit operators around the world, that the fiber-rich operators are about 1 year to 18 months advanced in the evolution of the network topology compared to those that don't have fiber-rich environments, where they're doing a lot of third-party backhaul or limited in their bandwidth capabilities.
And so this is kind of a follow-on to that, is what will the next 5 years look like for network densification?
You know, again, a tough question, but certainly if you want to provide the speed, bandwidth, and features that's going to be required in the future, you have to be a 5G player. And in order to compete against the other operators that are evolving their network in this direction, you're going to have to ante up and evolve your network and try to stay at pace with the other operators in the world. And of course, there will be new participants. It's a good question of, will the cable companies acquire other companies or also compete in this area and start ramping up their investment? So it's a considerable investment to evolve your network, and I think the only thing that's really holding back 5G right now is the adoption of the technology, get it tested and proven, and for the handset technology to catch up to the radio and the network technology, that may take a couple of years.
Yep. So here's another question from the audience. This one's for Barry. Follow up on gateway clock. So what does gateway clock buy? Whoops, I lost the question. Oops, sorry, I lost that question. Anyways, I'm not sure how I can get that back. Oh wait, let me look under, oh, here it is. Okay, sorry about that. Okay, follow up on gateway clock. So what does gateway clock buy me if it's just another clock that will contribute to the total TE budget, other than fixing asymmetry issue?
Okay, I think it kind of goes to the network planning rules. And what we recommend to customers is for phase delivery in the networks, you need to engineer your network from the endpoint back towards the core. And what we find, and where the standards are trying to set up, is the flexibility to use your core clock, establish intermediate clocks or gateway clocks as we call it along the way. But the key kind of engineering principle is to engineer your error budget from the end use point back into the network, and depending on what your transport feeds look like, that tells you how many hops, if you will, you can go. If you can, if there are segments of your network where you can reach all the way back to the core clock, job is done. You serve the PTP flows from the core clock. What we find in practice is in many cases that you need to have these intermediate clocks, the gateway clock, to establish synchronization point from there with the PRTC, the primary reference time clock traceability. So that establishes the origin of the flow at that 100 nanoseconds origin, and then you have that error budget from that point forward. So the gateway clock really buys you the ability to use your existing transport networks, locate a smaller, lighter weight clock out in the aggregation points that can feed timing from that point forward in the network, so that you, for cases where you can't reach all the way back to the core clock. So it really is a flexible kind of planning tool that allows you to take backup from your core clocks with the calibration that it does across the network, and then provide a protected source clock forward into the network.
Okay, thanks. We have about 5 minutes, so maybe take a few more questions. Here's one for Barry or Jim. Could you give examples of major operators using PTP technologies?
Yeah, this is Jim. I'll try to answer that one as best I can. I don't know how much we can say on specifics because we do have a lot of NDAs in place with a lot of operators. But if you look at 1588 or PTP in general, there's really segregation in the marketplace from a global perspective. In the United States, we have E911 requirements for location or positioning. So in the United States, typically GPS has been used as the primary source of timing in a base station for many years because it gives you the timing and it also gives you an accurate position. And PTP is generally, from a macro eNodeB perspective, been used as a backup. So in that regard, you know, AT&T and Verizon are certainly using PTP already. But for most of the global markets, if you go to Latin America or Asia or Europe, PTP has been used as the primary source of frequency timing or synchronization for many years already. We have deployed about 20,000 grandmasters and over 450 networks globally already. And we see PTP gaining more and more momentum, especially as the time error performance related to the emerging phase requirements for LTE-Advanced features and for 5G, we see that as the time error performance gets better, PTP performance improves dramatically, and we see PTP along with synchronous Ethernet as probably the main vehicle for timing based on a network timing delivery service model.
Okay, and I think this could be our last question. Any ideas how many hops, routers / switch you can have between GM and 5G base station with PTP enabled in the network?
This is Jim. I guess I'll try to answer that one as well. If you look at some of the latest information out of the XRAN, they're saying you really shouldn't try to go through more than 2 switches, whether they're telecom boundary clock switches or not. I don't think makes much difference because some of the new low latency switches, time error performance is phenomenal. But in that front haul market, they talk about PTP delivery currently in the documents they're creating, you know, no more than 2 switches. I think that will depend a lot on how good these switches get and whether you use full on-pass support or partial on-pass support. That key is the time error performance through each switch. If we can get down to 10 nanoseconds per switch, obviously you could go more than 2 switches between a grandmaster and the slaves themselves. So I think this is an area where the technology is getting better and better. And as this emerging technology gets tested and verified in the labs and moves into field trials, we'll be able to figure out in more detail how far can you actually stretch that path between the grandmaster and the PTP slave.
Yeah, this is Barry. I'll just add a little aspect to that. As Jim touched on that, you know, we're seeing, quite frankly, phenomenal performance from the latest generation of switches that we've been able to test in our labs. So that will really help the deployments a lot. What we recommend, you know, to all the customers engineering their specific networks is they go through a measurement phase where they really profile, okay, what are the switches we're using? You know, what do we have in those switches? I've seen some questions about the transparent clock or TC versus the boundary clock. Those are 2 different tools. A transparent clock can sit in the network, and its job is to try to calibrate out or measure the transit time to take the little transit delays out. The first standards that came in were supporting what's called a BC or a boundary clock. That does basically the same thing, just a little differently. It sets a boundary that it you know, is a full slave clock to the grandmaster above it, and then it acts as a master to everybody below it. So both are forms of on-pass support, as we call it, and we recommend really to look at do you have that in your switch? Can you enable it? And then with the high-speed switches we're seeing today, the next question is do I need to add it or not? So there's There's always an engineering phase for your network, and that's where you really want to take advantage of some of the measurement capability and monitoring, as we discussed in the tools earlier, that can help you make that assessment. So you can set good engineering rules for your network and really know that you've engineered good synchronization primary and backup flows in your network. And then once you go live, then you want to be able to let the equipment just monitor that and report any deviations or actions that you need to take in the operational phase.
Okay. Well, with that, it looks like we're out of time. Once again, I'd like to thank our panelists, Barry Dropping and Jim Olson from Microsemi, for your presentation and your insightful comments. This has been a very dense subject, so please, everybody, go back onto our website and re-watch it as needed, or download the slides. They will be up on our website shortly. Thank you to the audience for submitting great questions. And I've been your host, Susan Rambo. Thanks again to everyone, and have a good day or evening, wherever you are in the world.